Dr. Hassan Azad has accepted our Hassan
Hassan
Azad
Azad, yes.
accepted our request for being a speaker. It was a long-awaited talk because we were waiting for Hassan to get settled. I think I sent like two invitations before to Dr. Hassan, but he was busy or he was a kind of taking time in order to accept our invitation. But he's a regular kind of a regular participant featuring in our different seminars and for the youngsters who are here, this is really very important to get familiar with Dr. Hassan Azad. Probably he's the only one who is working in this area of Lie algebra in Pakistan, and he has such a wonderfully established career in this particular area. In my career, I haven't seen much algebra people as motivated, self-motivated as Hassan is, because he has a very unique style of pushing himself to step to do important thing in algebra. Today, he's going to present a particular problem, which is uh, which is very very interesting, and I think it took Hassan 2 years or 3 years to solve this problem, and he was very happy. And the moment he shared the news with me, and that is the moment when I said, now you have to present this problem, and he's super excited to present this particular problem. So over to you, Hassan, and thank you
Thank
very much
you.
for accepting our invitation.
Thank you, Imran. But no, it turned out to be something very simple. So, so the title of my talk is Semi-Simple Algebras of Vector Fields in C3. By the way, I have 50 minutes, right?
Yes, you have 50 minutes, Hassan.
Okay. So, I'm not going to give any detailed proofs, but I will explain the basic terms after giving a brief history of the subject. So Sophus Lee invented this theory of Lie algebras to understand basically differential equations, and where do all these different substitutions come from? And so one of his main results of Lie was complete classification of vector fields in the complex plane. I will explain in what sense he meant. What was his classification? In what sense? Okay, that will come later. And then this was extended by um, um, Gonzalez, Olver, and Kamran to vector fields in the real plane. Okay. So, and by the way, so there's an English translation available, and that is so English translation of Lee's is available online. It's called Sophus Lee's 1880 transformation groups paper. Sophus Lee's 1880 transformation groups paper. And it's by Ackerman and Herman. So that naturally suggests What about the corresponding result in 3Ds? So, I tried, and it's very hard. I did not get anywhere even for nilpotent algebras. But um, what turns out that for semi-simple algebras, it is manageable, and that's what I'm going to talk about. And uh, before I give any mathematical details, I would like to define for you the basic terminologies. So, basic. So, what is a Lie algebra? So, this is um, uh, a Lie algebra is a vector space, of course, over a field F, together with a bilinear form. Bilinear form B, which satisfies the following properties. The following properties. So writing bxy as x bracket y, we require x bracket y is equal to minus yx, or more generally, x bracket x is 0 to take care of characteristic 2, but let's forget about that. And then it satisfies this so-called Jacobi identity. X bracket yz plus y bracket zx plus z bracket xy is equal to 0. Okay. And here are some key example. This is all. So the first example is GLB. This is all linear transformations. All linear transformations on a vector space V. And if xy are linear transformations, we define x bracket y is x composes y minus y composes x. So this is the first main example. And then the other most important example, and that's what the whole of this lecture will be concerned about, is vector fields, the Lie algebra of vector fields. Of vector fields on an open set U of Rn. So, so a vector field is just a vector valued function. So a vector field V is a vector valued function. And of course, when I say a function, I mean functions which are you can differentiate as many times as you like. So if V, so what we do is to V we associate this operator associate the operator dv, which is the directional derivative directional derivative in the direction B. So if V has components F1 up to Fn, dVf is of course gradient of V, gradient of F dot V. So this is sigma Fi partial F by partial Xi. So we identify V with this operator. And then we can define a Lie bracket. So if D1, D2 are two such then D1 bracket D2, same as before, D1 composed with D2 minus D2, D1. Okay. And now, and then there are other interesting examples. For example, if you take an affine variety over the complex numbers, you have its algebra of regular functions, and you can look at all the derivations of this algebra. So that's even more general somehow. No, I don't know whether it's more general or not. No, it's not more general, but it is an example. Okay. So now, Lee's classification is in the local sense. This means that two vector fields are equal if they are equal on some open set. So in this sense, for example, if you take a single vector field, everyone knows that away from its singularities, you can write it as partial by partial x. And if you take, let's say, two vector fields which are commuting, and their rank is 2, then in suitable coordinates, you can write them as partial by partial x and partial by partial y. So in that sense, his classification is there. And Lie classified all finite dimensional algebras of vector fields in the complex plane. I will not talk anything about his classification in general, but I will talk about what is the analog. I mean, for the semi-simple Lie algebra, what is the classification? So first I have to define for you a semi-simple Lie algebra. Well, everyone, it's the same as in algebra. Whenever we have some structure, we say that it's a simple if it has no ideals. So in the same sense, a semi-simple Lie algebra is an algebra which has no proper ideals. So in this sense, Lie's classification is this. It's remarkably simple. Of semi-simple algebras in C2. So C2 means those which are defined on some open set of C2. So semi-simple algebra can only be either SL2C, SL3C, and SL2 cross SL2. So as simple as that. Okay. Now to state my own results, I need to define one more term, which is a Cartan algebra. Cartan subalgebra. Okay. So I will not define it in general. I will only define it in terms of semi-simple ones. So so it's a Cartan algebra, Cartan subalgebra. Let's be even more simple. A Cartan subalgebra of a semi-simple linear algebra, semi-simple subalgebra of GLV is a commuting algebra of diagonalizable elements. Of diagonalizable and in general you take the adjoint representation. So if L is some abstract, the transformation add from L to GLV, which is defined by add of x applied to y is x bracket y, is a linear representation, and then you can talk about commuting subalgebra of add diagonalizable elements. So maximal one. It's not. I gave a wrong definition. Cartan is a commuting algebra of diagonalizable elements, and which is maximal. Which is maximal. Okay. So now here's a surprising. Here's some results. This is jointly with Biswas and Fazal Mohammed. Let L be a semi-simple algebra of vector fields in Rn, which has a Cartan, no, not Rn, Cn. Which has a Cartan algebra of dimension n. Okay. Then L is a sum of SL Ki plus 1, where sigma Ki is equal to n. So it's very similar to Lee's. Only SLs are appearing, and if you assume that you have a Cartan algebra of dimension n, then it's a direct sum of the special linear algebra. Special linear means of trace 0. Okay. And in general, now for C3, a semi-simple algebra let me put it simple. The only simple algebras which can occur which can occur are SL2 cross SL2, SL3, and SO5. Okay. So, so to prove this, as I told you, I'm not going to give you any proofs, but I'll explain to you what are the main tools. Any questions so far?
Yes, Hassan. Sorry, ये एकदम मीटिंग डिस्टर्ब हुई थी.
Mm-hmm. अच्छा.
Uh, we are back again, I think.
Okay. Oh, so I was just that's why.
नहीं
So
नहीं नहीं. We attended up till here. We attended up.
अच्छा अच्छा
एकदम
अच्छा
हो
तो-
गया. But
अच्छा
there's one question by Mohammed bin Nasir.
जी जी जी
जी Mohammed Nasir.
जी मोहम्मद.
He can't unmute. एक minute. Yes. Okay, you can unmute yourself, Nasir.
Hello, sir. Sir, I
जी
have
ना
a question.
हम्म.
Sir, you just mentioned that we have only simple algebras which are SL3C by
Oh,
SL3C.
so my mistake. Semi-simple ones. The
Yeah.
only semi-simple.
Okay. Okay.
Otherwise, you see the right here a mistake. SL2 cross SL2.
Yes. Okay.
And then there should be more. There should be okay. Let me correct it. Which this only simple. Otherwise, I'll have to R R R SL2 SL3 or SO5. Now it's okay. And
Yes, sir. Now it's
the semi-simple ones will be, for example, SL2 cross SL2 or SL2 cross SL2 cross SL2 or yeah, thing like this, and then these other ones. Or like SL2 cross yeah, only SL2 cross SL2, SL3 and SO5. Yeah. Mhm. Okay. So what are the main tools? So the main tools are number one is the local canonical form. Of semi-simple algebras of vector fields. This is one. And the second is representation theory. Not many, just the basics. And the third is root systems. Because we are semi-simple stuff, so we have to use the root systems. So local canonical form, they say that if L is a semi-simple algebra of vector fields, and Cn, and H is a Cartan algebra, Cartan subalgebra of L, then in suitable coordinates, it's a Cartan subalgebra of L of dimension small n, then suitable coordinates, this Cartan algebra is suitable coordinates. H is partial by partial x1, partial by partial x small n, and L is generated by vector fields of the type e to the xi vi e to the power of minus xi vi, where vi's are fields whose components are independent of x1 up to xn. So this is one of the main tools which I use. And at the end, I will give you, if you are interested, I can give you the references. And then the second tool is elementary representation theory. Can everyone hear me, or are we still yeah.
So that
I've said that I first stated the results of Lee and then my own results. And for semi-simple algebras in R3, it's quite simple. And then I gave a general result for semi-simple algebras of vector fields in Cn that have a Cartman algebra of dimension n. They must be a product of SLs. And the tools which we used are the local canonical form of a semi-simple algebra. And then the other tool, which I'm going to discuss now, is elementary representation theory. And the last one is root systems. So root system, they come up in very unexpected places. Recently, in the theory of cluster algebras. So I'm going to spend a little bit of time on root systems. So in case somebody wants to get into cluster algebras or wants to follow up what I'm doing, then hopefully this will be easier for you. Okay, so yeah, so what's the main result of representation theory? If L is semi-simple, and rho from L to GLV is a homomorphism, is a representation in GLV means a homomorphism of Lie algebras, is a representation, then every invariant subspace has a complementary invariant summand. Okay, and then this is the first point. And the second is fix a Borel subalgebra. This means a maximal solvable subalgebra of your Lie algebra. Okay. Let's fix a Borel subalgebra. Let's call it B, and let n be the derived algebra of B. Then in every representation, there is a vector V such that such that rho of x applied to v is equal to 0 for all x and n. And the number of, this is not important, but it's useful that the number of irreducible summands is exactly the dimension of this vector space. Okay. So these are from the theory of representation which I have used. And then the perhaps the most useful tool is the theory of root systems. And as I said, they keep on coming up in very unexpected places, and most recently in the theory of cluster algebras. So first of all, a reflection. So V is a vector space, is a real vector space. A reflection rho is a transformation such that rho square is equal to 1, and it's non-trivial transformation, so its eigenvalues are 1 or -1, and the -1 eigenspace is one-dimensional, and of course, and +1 eigenspace is a hyperplane. Okay, and then if you take an inner product invariant under this reflection, which is very easy to do, then the formula for rho is this. Let rho of alpha be equal to minus alpha. Then rho of x is equal to x minus 2 times inner product of x alpha divided by alpha alpha times alpha. And we write this as x minus, and we write it in, I don't know, what are these brackets called? Okay. So a root system is a finite set of course of non-zero vectors, which is invariant under is a fine set R, which is invariant under all the reflections rho alpha x is equal to x minus 2 times x alpha over alpha times alpha. Here this the inner product is one which is invariant under all the reflections. Okay. And then we assume one more condition, the only multiples of alpha.
वैसे परेशान जाने से मसले कोई नहीं हल होते
क्या कह रहे हैं?
कोई बेहतर फैसला करो
पीछे कोई आवाज आ रही है इमरान.
I unmute them. Aksa, please keep yourself muted.
The only multiples of a root is itself and its negative. And the most important is the integrality condition. 2 times 2 times alpha beta over beta beta times beta. This is always an integer for all alpha beta in R. And all such have been classified. It's one of the main results in theory of root systems. If I think who classified them first? I think Coxeter and Van der Waarden, I think. I'm not sure. So the 2D, yeah. Oh, then there's a very important notion of positive roots. So fix the basis. So this root system R lives in some vector space, some vector space V. Fix a basis. Fix a basis E1 up to En of V. And so every root R is sigma xi ei. We say that R is positive. R is positive. So we take the lexicographical order. If the first non-zero entry xi is greater than 0. And then negative is defined analytically. The first non-zero entry is negative. And we say a vector is a positive vector, a positive root is simple if it cannot be written as a sum of 2 as a simple. It's simple if it cannot be written as a sum of 2. Sum of 2 roots. So here are the 2D systems. So A2 consists of roots alpha, beta, and alpha plus beta. And then B2, alpha, beta, alpha plus beta, alpha plus 2 beta. And G2, alpha, beta, alpha plus beta, alpha plus 2 beta, alpha plus 3 beta, and 2 alpha plus 3 beta. Here you have, in the first one, you have alpha, the product of the Cartan integers is 1. Here alpha beta times beta alpha is equal to 2. And here alpha beta times beta alpha is equal to 3. Okay, so this fixes the angle between them. I'm not going to waste any time in drawing them. They are given all over in every book. Okay, now the interesting thing is that if I give you a root system, it's very easy to write down a real algebra with the corresponding root system. So here's the construction. How much time do we have still?
Still you have 10 minutes.
Oh, then no. Then I cannot do this. Then I have to wind up. I will not construct it. Okay. So now, knowing all these types, knowing all the types of subalgebras of vector fields, in C3, how do we realize them by actually realize them as vector fields? This is a non-trivial question. So there are two ideas. Every simple algebra other than SL2 has a so-called, when has a so-called Heisenberg algebra, but we are not doing any physics. This is just, it means a 3D non-solvable algebra has a 3D non-solvable has a 3D non-abelian, has a 3D non-abelian algebra, which has an abelian algebra of rank 2, means we can introduce coordinates. We can introduce coordinates x and y, x, y, z, so that partial by partial x, partial by partial y belongs to the Lie algebra. Now you're left with only so you should use the commutator relations, and then you'll be left with ordinary differential equations, and you solve them to find them. So that is one idea, and the other idea is that let me check what yes. In case the algebra contains SL2 cross SL2, one can introduce coordinates in which the Cartan subalgebra of this one is partial by partial x and partial by partial y, and again this reduces the problem of realization to solving ODEs. Okay, so this is how you prove that. B2 and G2 cannot be realized as vector fields in C2, and G2 cannot be realized as as vector fields in C3. Yeah. So now the problem is, what can we say about the similar problem in vector field in R3? We know that it has to be a real form of these complex vector fields, but it's not entirely straightforward, because there's a realization of SL2C as vector fields in C, but there's no realization of SO3R as vector fields on the real line. So there's a realization of SL2C in the complex line, but there's no realization of SO3 as vector fields in R1. So one needs some small idea to do this. And so here are some references. So the first one is equality of algebraic and geometric ranks. Geometric ranks of Cartan subalgebras. And applications to linearization of a system of ODEs. So I will not write down the whole title just to save time. This is sections 2 and 3 for local canonical form. And embedding algorithms and applications to differential equations. This is section 2 and section 4.1, 4.2, and 4.3 for roots. And on Lee's classification, of subalgebras of vector fields in the plane for classification of solvable algebras. It's very technical, but it's not too hard. I think it's a 15-page paper. And all these papers are by myself and my co-workers like Waqas and Indraneil, Sajid, and Fazal Mohammed. And then, of course, there's this Gonzalez, Kamran, and Oliver, Lie algebra of vector field in the real plane. So when you Google the title, you will get these papers. So this is all I had to say. Thank you.
Thank you, Hassan. Thank you very much. Are there any questions? Saqib, you wrote a question which was somehow related. What was your question? May you repeat it again? Saqib, can you repeat your question again? So are there any other question from the audience? Unmute yourself. Oh, you can't unmute yourself.
Now, if you
Okay,
give
now
them,
you can. Okay, now you can unmute.
In the definition, I had a question that what do you mean by the invariant complementary invariant summands?
Oh, okay. It means who's asking this question?
Saqib, Mohammed Saqib.
Okay. So you have a representation of the Lie algebra into some GLV, right? And suppose W is L invariant, means rho x v belongs to rho x w belongs to capital W for all x in L and W in capital W. So this is invariant, right? Then you can write V as W plus W tilde, direct sum where W tilde is also invariant. Saqib, is it clear?
Yes, sir.